Hi, this is Team 18 of ISD 528, and this is our DfM project final presentation. Our team consists of Emil, John, Mark, myself, Mike, and Sarthak. This is the agenda we will be going over for our presentation. For product description, we are evaluating a meat grinder for a design for manufacturing, design for assembly. For operation, food is placed into the inlet plate where it will travel down the funnel and is fed into the chamber with a screw conveyor that is powered by an electric motor. The conveyor knife and screw shears, mixes, and moves the food through the tube grill to be extruded out of the grinder. Primary uses are chopping, mincing, and or mixing raw ingredients such as meats, vegetables, and animal feed. This is our finished assembly view that shows a CAD model of our meat grinder with callouts of all the major components. This is an exploded assembly view, again a CAD model with the callouts of all the major components. For primary and secondary customers, our primary customers are commercial grade kitchens and restaurants that typically deal and process high volumes of meat and vegetables. Secondary customers are the smaller local independent butchers, artisan shops, individuals who want to process their own meat, and that typically process lower volumes of meat and vegetables.
Next, we have fast diagram. Our primary functions are intake food, processed food, assure convenience, enhance product, assure dependability, and please senses. These primary functives are then mapped to the secondary functives by how and why relations to define overall functions of the machine. Coming up next is function component mapping matrix. 16 parts of our machines are mapped to functions defined in fast diagram. The updates given in midterm report are incorporated and highlighted in red color. Example, motor was removed from functive improve stability. Next we have function differentiation table. Here functives from fast diagrams are divided into two groups depending upon them being same or different for primary and secondary customer groups. Next coming up is component commonality table. Function differentiation table was used to prepare component commonality table and parts were defined for platform and modules. Next we have platform common interface. According to component commonality table, we here have the common interface parts among the primary and secondary customers. Next coming up is product variant component differences. This parts maps to the functions unique in two customer groups: motor, inlet, plate, grill, knife and screw provide better versatility while working for different requirements of different customer groups.
This is our product family assembly diagram. The diagram has been modified to delay differentiation by a few steps. As you can see, platform parts are brought earlier into the assembly process, while the module parts are pushed back towards the end after differentiation. Onto the DFMA focus analysis, the quad chart shows that there are 4 high cost, high importance parts, with the assumption of high cost being anything over $5. This also reveals several low cost, low importance parts which will be redesigned. The redesign for manual assembly has 2 main improvements, the first one being the combination of the rubber leg and the leg screw. This consolidates parts and utilizes a snap fit to eliminate fasteners and reduce part count. The second improvement is the redesign of the conveyor knife, which reduces insertion alignment difficulty by increasing the symmetry of the part. Finally, the design for manual assembly analysis reveals that the total manual assembly time is reduced by about 43 seconds. The manual assembly efficiency increases by about 16.5%, and total assembly cost is reduced by about $2, giving a final total production cost of $121.91 for the product.
Here you see the design for automated assembly. In the top left, labeled number 1, you see our original fishbone assembly diagram. Following that gray arrow from the top left down to the bottom right, you see number 2, our fishbone assembly diagram after redesign for manual assembly. Manual assembly resulted in the combination of rubber legs and screws, which happen to be a subcomponent to our motor case bottom subassembly, which is seen above. The actions we took for redesign consist of DFA 1, reduce part count. This was accomplished by combining the cord protector and motor case bottom. DFA 2, reduce fasteners, which was accomplished by combining the screws and rubber legs, which also introduced DFA number 3, snap fit features. DFA 6, increased symmetry, was accomplished by replacing our rectangular on-off toggle switch with our simplified circular power button. In DFA 7, facilitate orientation was applied to our motor, which allows the motor to be assembled 180 degrees and still function properly. Looking at the analysis, the before redesign total assembly cost resulted in $3.30. After redesign resulted in a total assembly cost of $2.09.
From the primary product variant, we had redesigned two components for manual assembly. We chose those same two components to be redesigned for manufacturability. The first component after redesign for the leg, we decided that the key dimensions were those features on the snap feature, which overall fit to the motor case bottom to ensure stability of the assembly. The second component was the conveyor knife, which we chose the key dimensions that interact with the other components as this component spins in the assembly, which allows for the shearing and compression simultaneously of the food. So the blade major diameter, which spins freely in the tube, and the edge length, which controls the interface for the conveyor screw. With these, we identified the tolerance that would be acceptable for all of these dimensions to ensure proper function, and then utilized the shape and mass of the components, the thickness and tolerance, as well as the surface finish, which we viewed as not important or not critical, and the batch size to define what processes were suitable to manufacture these parts. Injection molding and machining were suitable for the leg, but we recommend the injection molding to be used because of the snap fit features. And sheet forming and machining were suitable for the conveyor knife, but we recommend the sheet forming because of the economy of scale. For the conveyor knife, we redesigned this part for optimized manufacturing by utilizing the design principles of a standard punch in the central cutout, 0.8 millimeter radius on all of the exterior corners, and then offsetting the hole to never drop below the thickness of the part. With this, we were able to develop an analytical and a quoted savings, with these optimizations in place, and we found that the analytical savings are around 39 cents a part, and the quoted savings are around 25 cents a part. For the leg with injection molding as the manufacturing process, the design guidelines that we integrated for optimization were to integrate fasteners, removal of sharp corners around the edges, and then ensuring that our rib to wall thickness ratio was approximately 60%. With these optimizations in place, we found an analytical savings of approximately 4 cents per part. For a design for product service system, we primarily utilized services to the customers, which include a return policy, warranty, and then maintenance sign-up program. But we also utilized increasing of shared use, which includes refurbishment of some of the components that are meant to be sharper, as well as dematerializing and making sure that customers are receiving a user manual in a PDF format rather than a booklet. And this ties into our environmental impact, which we have primarily utilizing recyclable parts and reusable parts, and ensuring that the packaging happens in eco-friendly materials. So in conclusion, our total cost reduction was a little less than $4 per assembly, which equates to $186,000 per year when you account for the 50,000 annual units. This contribution was largely in part from the assembly, but we also did get some contribution for the manufacturing improvements as well. The pros of our design were that we did widen the group of users able to use this and overall reduce the part count and complexity of the assembly. But overall, we weren't able to redesign all of the high-cost, high-function components and did have to dip into some of the low-function, low-cost components for redesign. Looking back, what we would do is have a greater differentiation between our primary and secondary customers to get the best benefit, of the product complexity. Thank you.